today we've got Alan Green, who wants to, well, I've asked him to outline some of the most interesting things in the world as far as I'm concerned. So we bumped into Alan when we were doing the Renewable Fuels Week in Canberra a couple of weeks ago. And our project Beyond Fossil Diesel lines up, it ended up sponsoring that Renewable Fuels Week in part. And what we had was a presentation, but sharing the stage with Mike, who did the presentation on behalf of DPI, was Alan. And it turned out to be one of the most interesting speeches of the day, or presentations of the day, because of the possibilities it opens up for agriculture overall. So I think it's important that we understand the role that agriculture can play in this sort of whole new future fuel sort of world. And it seems like Alan's the best person to talk about that. So I'll flick over to you, Alan, if you're happy to take off.
Thanks, Jock, and thanks for the opportunity to speak to you and your colleagues about this. It's, as you've said, it's really a reprise of the talk I gave in Canberra at the Renewable Fuels Week. I won't go into introduction of myself. The notes for the meeting have a bit of my background, but I did spend all of my research career developing new oil crops and plant oil technologies. And as I said in Canberra, I think that gives me a bit of a different perspective on what's in the pipeline compared to some of the discussions that people are having around how we source feedstocks and processes to make renewable fuels. I think it's a particularly important time at the moment as we're in the middle of the consultation and development of the sector decarbonisation plans for the 6 industrial sectors. Just today we had the federal government release its draft roadmap for the transport and infrastructure sectors. And that's obviously one which is heavily dependent on fuels, and therefore renewable fuels are really important in that pathway. And look, I think it's really important that those who are designing these plans and making policy and implementing industry support packages, etc., which are going to go into the medium term, not just this budget, that they have a full understanding of what are the potential pathways that we could use to supply renewable fuels in the future. I think there has been a little bit of a too much of a focus on some of the hoped for future fuels built around hydrogen and carbon capture into e-fuels, etc., and not enough focus on what we can do immediately with the fats and oils feedstocks that we have available and that we could expand. And it's very critical, I think, from a climate change perspective, emissions reduction, that we start the transition as early as possible. So there's a high sense of urgency, particularly seeing we've been so late into the game. And I wanted to get these opportunities for fats and oils feedstocks really on the agenda for people making those decisions. So I will basically run through that talk, but I thought let me see now. Am I getting advanced? That's right. So this is a situation for Australia's use of petroleum fuels, about 50 million metric tonnes per year, and that's 37-40% probably of our energy consumption in Australia. So it's a big piece of the emissions challenge. There is a petrol component. There's a large diesel component in Australia because of the industrial use and farming use. 2 million tonnes of it is just used directly in agriculture. There's the jet fuel and the marine, and there's the little talked about but important carbon-based chemicals that support the industry. So we import 95% of our petroleum products. That's a very insecure situation for us. We've been in that situation for some time, and we really have to get a domestic fuel supply if we're going to have sovereign security. And it doesn't make sense to make that a domestic petroleum supply. We have to have a domestic low carbon emissions industry, and that's renewable fuels. So what I want to do is try and step through how we could make a significant proportion of the diesel replacement component. So diesel, jet, marine fuels are all similar types of fuels and different to gasoline, petrol. So I'm not going to talk about the ethanol, petrol sort of market here today. I'm going to stick to my lane around the fats and oils that are feedstocks for diesel type fuels. But I thought I would just step back because I don't know much about the audience today and what their background is. So I just thought I would step through a couple of slides to just show you how big this challenge is globally. If we're going to move to a zero emissions economy, we have to replace petroleum. We have to move to a post-petroleum era, basically. And we currently globally consume 5 billion tonnes every year. That's 100 million barrels of petroleum every day. I've just tried to scope this out to show you what sectors of industry that gets used in. And so each one of these barrels is 50 million tonnes per annum. There's basically 100 barrels there. So each one's 1% of supply, if you like. And the great majority goes into petrol and diesel production for automotive use. That's about 75% of the total consumption of petroleum. Another 12-13% goes into liquid fuels for aviation and marine, and the equivalent amount in total goes into chemicals, through petrochemicals into industrial products, chemicals and coatings and polymers, etc. And if you compare that to how much renewable oil we produce from our oilseed crops, currently that's about 200 million tonnes annually. So the 4 barrels down the bottom in orange. So you can see that there's actually no way that we could expand our oil crop production to replace all of petroleum usage. It's just not possible. But of course, the good news is we don't have to. And that's because, this 75% of demand in the automotive sector is going to become effectively decarbonised. That's compared to a renewable fuel where we use carbon that we're recycling from the atmosphere, previously released carbon. With true decarbonisation, we move right away from carbon as the energy molecule. And so electrification is going to be carrying out most of the decarbonisation in this sector. And so EVs are obviously the most prominent route to doing that. We have to remember, though, that relies on a grid which is not 100% renewable. So, when we switch to an EV with a grid that's still 60% fossil fuel, we're moving some of the emissions back to the power plant rather than out the tailpipe, if you like. But there are. Excuse me, I just need to go back. Yes, that's better. There are routes where we can get 100% of emission reduction by direct solar to EV charging, and a lot of households are doing that, where they have their own solar panels that charge their vehicles overnight, and that's truly 100% renewable, low emission. So I think we can rely on decarbonisation in the long run for replacing the vehicle market, fuels for the vehicle markets. But that transition is going to be very slow in Australia. We've had a period of active political opposition to EVs, so we've got a late start in that transition. We still have opposition to it in a lot of aspects of policy. We have the high emission electricity grid, as I've said, and we'll have a slow retirement of the legacy internal combustion engine vehicle stock over a decade or more. So there's going to be a large proportion of the emissions that come from that automotive sector that we still have going out for a decade or two, unless we abate those by having renewable fuels in this segment of the market. So I think it's an often overlooked area with all the focus on aviation fuel, SAF, sustainable aviation fuel, and marine fuel, that most of the emissions reduction we could do today would be by replacing diesel and petrol with renewable diesel, biodiesel, and ethanol in our current automotive transport. So I don't think that should be lost by policymakers as an opportunity. So if we move to the other sectors, these are often called the hard to abate segments because we can't really replace these with electrical supply. Aeroplanes and particularly long haul flights and shipping rely on liquid fuels, and so we have to replace those with renewable versions of those fuels. And of course, the chemicals that we use, we're a carbon-based society. We're not going to move away from that. We're still going to need all those carbon molecules, and they should come from renewable sources rather than from digging up new carbon from below the ground. So just quickly to give you the figures on those, global aviation fuel consumption is about 350 million tonnes per year. You can read through those points in the presentation after, if you like, and just to say that there's multiple feedstocks that we can use to make renewable sustainable aviation fuel. And there are different processes to take those bio-based resources through to fuels. And we already have flights happening commercially now with 50% sustainable aviation fuel in their tanks, and that's increasing. And flights have been tested with 100% sustainable aviation fuel. The main problem here is the feedstock cost compared to petroleum and the availability on enough scale. A similar situation with marine fuels. It's about 250 million metric tons per year globally, and these can easily be replaced by biodiesel and renewable diesel alternatives. The US Navy, for instance, had a program to transition their Greater Green Fleet to 50% non-fossil fuels, and so this is certainly an addressable part of the market. I won't go into the bio-based materials, but there are plenty of opportunities to produce petrochemical equivalents based on biological resources to replace petrochemicals with effectively an expanded oleochemical industry. So if we add those three areas together, there's about 1.2 billion tonnes in total of renewable carbon oils required to replace all those by 2050. That's about 7 times our current plant oil production, which is a very big ask, but I hope to explain to you some technologies that will help. But it's $1 trillion bio-based opportunity globally, so it's a real potential for agriculture as well as a challenge for society. I think it can be done, and I think there'll be no one silver bullet solution. We're going to need a portfolio of multiple solutions to get there to that global objective. Okay, so just coming back to the Australian situation, I want to go through 4 ways that I think we can make big inroads into that diesel and jet, automotive diesel, jet and marine fuel market using our current technologies in agriculture. And technologies which improvements which are coming through the pipeline now, and which, you know, I think most of the policymakers in this space would not be aware of some of these technologies, and so it's important to get them into the mix, and I hope to do that by doing talks like this. So thanks for the opportunity. Again, not sure that everybody knows the pathways, so let's just summarize it this way. There's a whole range of pathways of going from agricultural biomass through to fuels. The ones which have been most prominent in the past have been a biodiesel, which is a straight fatty acid methyl ester derivative of seed oils predominantly, or fats from animal products. And that goes into the diesel replacement market, obviously, and ethanol going into the petrol gasoline replacement. Ethanol is originally derived by fermentation of grain products such as corn and cereals, but obviously that was having a big problem in the period around 2005 to 2010 with a food versus fuel tension there. And so people looked for alternative ways to use plant-based carbon and sugars to ferment to ethanol, and that's called cellulosic ethanol, or second generation, 2G on this diagram, where you take the more complex starch, cellulose, lignin, all the carbon basically in the biomass, break it down to simple sugars and then to simple C2s and through fermentation through to C2 to ethanol. So that's been the past situation up until about a decade ago. And then we've had developed since then ways that we can convert the oils substrates through to a renewable diesel or a sustainable aviation fuel, which is a jet fuel version of renewable diesel. Effectively, the difference in the process compared to biodiesel is that renewable diesel is completely deoxygenated, and it's a complete functional equivalent for diesel, and SAF is a complete functional equivalent, correctly formulated, for jet fuel. On the ethanol front, there have been technologies developed to take ethanol and to build that up to the same long chain alkanes that make up diesel, and so you can make RD and SAF by alcohol to jet, ethanol to jet, for instance, or methanol to jet pathways exist. The other approach is to take the whole biomass and put it through some pretty heavy deconstruction processes, and there are a range of pathways here. Fischer-Tropsch, the middle one in green there, is the most prominently known one, but there are others being certified now, and you can take effectively a low-grade feedstock in that case, a crop residue, for instance, in an agricultural setting, or a metropolitan solid waste, municipal solid waste, sorry, and you deconstruct that right back to short chain alkane molecules, and then you build it up much the same way as is done with the ethanol to jet to the molecules you want for diesel. That is a low-cost feedstock, but it's a high-cost processing system because there's a lot of energy required in that breakdown and build-up phase. Feedstock is low cost because it's a byproduct, although there are aggregation and storage and handling issues around that. It's not an easy thing to assemble enough in one place, enough feedstock to make a viable pathway. So that's got a distributed process as necessary there in an agricultural setting. In contrast, the fats and oils that I'm going to focus on are a high-cost feedstock currently, because those oils are currently produced mainly for food, and they're in the $1,000 to $1,500 a ton range, and we're trying to replace a petroleum product, and petroleum is in the $500 to $600 a ton range. So the challenge there is, how do you bridge the cost? And but the process itself is quite simple and straightforward. And this is the challenge for policy for government, is how do you implement systems which level the playing field on a cost basis to make renewable fuels made in this way equivalent price to petroleum fuels. I won't go deeply into that, but I'll touch on it again in a couple of slides. So that's hopefully a quick overview of the landscape for production of fuels from agricultural products, renewable fuels from agricultural products. And this is, I put this up because it came out in August last year, and it's been referred to quite a lot by people who are constructing policy. And I think it is, I don't like to be kind of not attacking, but criticizing a report from CSIRO, given that I worked and led a division of that organization for the last 10 years of my 40 years there. I don't want to be appearing to be a disgruntled former employee or anything like that. But if you look at the blue line across the bottom here, and let me know if any of these slides aren't projecting well enough, that is CSIRO's estimate in this report of how much fats and oils feedstocks from oilseeds could contribute to the demand for sustainable aviation fuel out to 2050. Basically, it's a projection, a flatline projection of the amount that is used today, and it doesn't take account in any way the opportunities to expand our production and to develop novel ways of producing those feedstocks in agriculture. That's my first concern with it. My second concern with it is that the green part of the curve at the top, which is power to liquid, also known as e-fuels, if you're aware of that. It's a case where you synthesize a fuel compound by using green hydrogen and captured carbon, both of which are struggling as technologies and have high high costs and low energy efficiency, low conversion efficiency. So although we can make e-fuels, I think there's a very big question mark around whether in the long term they will be economically or energetically viable, at least not until we are completely zero emission on our grid and we have surplus renewable energy such as wind and solar to go into other applications where price no longer becomes important, if you like, a main consideration. So, and the other thing about the report was these are the cost reduction curves predicted to 2050 for each of those pathways. And at the bottom, along the bottom, the purple dotted line is jet fuel, current jet fuel. And you can see the very optimistic cost reduction around P2L, e-fuels, and parallel kind of slopes for the other sources, and very little reduction in the vegetable oil cost of production relative to jet fuel. And I think there's cause for optimism that it can come down a cost curve as well. So I've been very keen to get this message out here as to what are the opportunities in Australian agriculture. So let's see how much feedstock we do have. And I'm just going to map out here what we produce in oilseeds, pulse and cereals nationally, and what we export and what we keep in country. So first of all, what do we keep in country? We have about 8 million hectares of our agricultural arable land devoted to cereal, oilseeds and pulses that remain within Australia for domestic use. We don't have any problem with domestic food security because this is only 1/3 of the amount of products we produce. There's another 17 million hectares of our arable land production, which is effectively producing the same products for export. So predominantly cereals. We're still a very cereal dependent country. Some pulses there and oilseeds. Now, the important thing around the oilseeds, we're exporting around 5 million tonnes these days. Canola and cottonseed, it's going up because canola has been booming, and obviously the surplus is going to export. And when we export those oilseeds, we export the oil component as well as the protein component, obviously. And that oil component is actually now being used in overseas markets to produce fuels. So we may think we're exporting food for global food supply, but we are actually currently exporting a lot of oil that's being used for renewable fuel production in other jurisdictions. And I think there is an argument that we should be able to retain that in Australia and use that oil to kickstart a renewable fuels industry and export the meal after it's processed domestically, because the meal is still in surplus to our needs, and there are strong protein meal markets nearby Australia. So we'd only really be retaining the oil component of those products. And so I think that is the first thing we can do to create a pool of feedstock that could be converted to renewable fuel. And that's 2.5 million metric tonnes. You know, that's 8 times what is in those graphs I showed you from the CSIRO report, and it's about half of the current jet fuel production possibilities. So that's my first point. We could do that today with the right policy measures. And what would those policy measures need to do? Well, the principal thing they need to do is to give farmers the same return for that grain as they get on the export market. There's no reason for farmers or traders to sell to the renewable fuel industry canola seed or cottonseed for less than they get in overseas markets for food and other product uses. So that will require the introduction of a system that levelizes those costs. And that's basically what's being done in several countries in the United States. They have a low carbon fuel incentive system, the LCFS and RFS in the USA. Canada has a system, Europe has a system. And these are ways in which bridging the cost of production gap between renewable fuels and petroleum-based fuels. And we will need to implement a scheme in Australia that achieves that if we're to utilise those resources for domestic oil production. And that's really what the government is considering at the moment. and they've announced in the federal budget and in today's paper that they are looking at a period of consultation with industry to decide, what type of schemes or support mechanisms would work in an Australian environment to achieve that outcome. So I think that's a good step forward, that's in play. Where it will end up will depend on a lot of the deliberations over the next 6 months. So moving on from the oilseeds that we currently export, what about the other 13 million hectares here of cereal production that we export as well? Could we use some of the land that's devoted to those cereals for additional oilseed production? And I think there is opportunity to do that. I think our agriculture could still benefit by increased diversity, crop diversity, so long as it's not a single species that gives us, too much of one crop and difficult production challenges around diseases, etc. But I think we could certainly move into that space with additional oilseeds. And the people that I've spoken to in the ag systems area think that systems with increased oilseed or potentially oil producing legumes would be an improvement over our current systems. And yeah, so I think I've just covered that point. Now, one additional way we can grow more oilseed crops, I should make a point at this point, we have to, as much as possible, not reduce our food production. We do make valuable contributions to global food supply, but it is only 2% of global food production. I think there is an argument that we should be able to redirect some of our food production to domestic fuel feedstocks in this period where we're trying to kickstart the industry and get it underway. But the expansion we'll have to do following that really has to be done by intensification, not by competition with food. And there are a number of ways we can intensify our production of oil-based feedstocks in our agriculture without removing food crops or outcompeting food crops. And the first way is to move into parts of our farming system where we don't currently grow crops. So you may be familiar that in the United States there's been this movement in cover crops, which is the production of crops in the period between summer crops, which is normally left fallow, but which the US government has incentivized having cover crops, just crops to keep the ground stable and minimize erosion, but not producing agricultural traded products. Farmers are subsidized by the US government if they grow just vegetative cover crops. Well, this is an immense area between corn, and if you think of all the corn and soy acreage in the United States, all grown as summer crops, that period in the middle is an enormous amount of acreage available for additional crops if they can fit within the fairly tight window, and if they can produce a grain crop or a vegetative crop in the winter conditions, in the cooler winter conditions. And these three relatives of rapeseed canola have been investigated for the last couple of decades and are now coming to market as short season, winter hardy crops that can fit into that US cover crop zone, if you like, and which are now opportunities also for Australia, but at different stages of development. New Seed is developing Brassica carinata, and that's under evaluation in Australia. It's in production elsewhere, and it's particularly in South America, and the oil is taken from the seed and used for sustainable aviation fuel today. And BP is the customer for New Seed's carinata. Camelina sativa is another relative in the Brassicaceae, and that's being developed by U10 Bioscience in the United States, and they're connected to Vision Bioenergy and the S&W Seed Company, a company that also operates in Australia, and Shell. And there's another program with Global Clean Energy investing in the United States. And recently pennycress, which has been developed previously as covercress by the company Covercress, is now being invested in by Bayer, and Bunge are the the downstream partners in that arrangement. So these crops are coming into production in the United States, and they will have opportunities in other parts of the world, including Australia. They will produce oils that will be suitable for industrial use as feedstocks for fuels, and mostly not suitable for food. So they won't be a competitive product. They won't be bid away by the food market, for instance. They can be a stable production base. So that's the second way, to grow more oil seeds by intensifying our agricultural system. And we don't need to just restrict that to those cover crops. We could do this by growing more canola. We could grow more Hyraceae juntia, that's Indian mustard, for instance. Or we could grow the cover crops carinata. In Australia, we could even grow some of the oil seeds that we've used historically, safflower, linseed, not so much soybean in Australian system, sunflower, for instance. They could all be in the mix of expanding oilseed production within our current farming systems. The second way of intensifying is to make our oilseeds make more oil in the seed, if you like. And so if you look here, our oil crops, canola, sunflower, peanut, safflower, they're basically in the 40 to 50% oil content range. Breeders have been very good at creeping that up from the low 40s over decades of selection. But they haven't yet reached the levels that we see in, say, sesame, 60%, or macadamia, 70%. So I believe there's technical scope to increase the amount of oil in the seed, and that this could be quite important for some of our low oil crops like soybean and cottonseed, only less than 20% oil, and potentially even lupins, which only have 8% and are never crushed for oil. Why do I think this is an opportunity now? Basically, these crops do not have enough genetic variation in them to achieve this by plant breeding, and that's why they hit these ceilings. But I'm going to show you a technology in a minute which has opened up the opportunity to genetically engineer oil production in any plant and in any part of the plant. And I think these technologies have a lot of opportunity now to be deployed in our oil seeds to increase that oil content. In Australia, for instance, we could, if we could do that with cottonseed, take it from something in the 18% range up to mid-30s to 40%. That would be a fantastic development for increasing oil feedstock. And in case of lupin, if we could develop that from the low levels of 8% oil up to the same levels that are present in, say, for instance, peanut, which is another leguminous crop, in the 40%, this would really open up another opportunity for Australian cropping systems, particularly with the nitrogen fertilisation advantages and the fact that lupin is our lowest value grain. It could very easily become a very high value grain. So these are really exciting opportunities to explore. So those two ways are ways we can expand our current oil production, maybe double it through a combination of those. But if we're going to take on the whole market, we need to have a massive step change in oil production. So we need new technologies. And we started thinking about this in CSIRO around 2009, 2010, in the midst of the food versus fuel issue. We asked, well, can we produce oil in agriculture in another way, not relying on our seed crops, which are our food crops predominantly? And our concept was, let me just show you this graph first to point to the opportunity. This is a depiction of the total amount of biomass in global agriculture, in cultivated agriculture. It's about 25 billion metric tons. The large chunk of that is in pastures and forage crops. The second largest is in cereal and coarse grain crops, about 5 billion tonnes of biomass and 2.5 billion tonnes of grain on top of that. And then the oil crops are only 1.5 billion tonnes of biomass and half a billion tonnes of grain and only 140 million tonnes of oil produced. So you can see that of all our biomass in agriculture, very little is devoted to oil production. So there's an awful lot of leaves out there that could be potential targets, and that was our premise. We thought about whether we could take the pathways that seeds deploy to produce and accumulate oil and express them in the leaves instead of the seeds. This is quite, off the wall thinking, because there are no plants that on the planet that we know of that accumulate oil in the leaves. They accumulate starch in leaves. They accumulate oil as a very dense energy source in seeds for germination, or in the case of fruits like palm, to attract pollinating and seed dispersal organisms that are coming, birds, etc., come for the energy in the fruit and take away the seed for dispersal. So we could do this, we could attempt this, because around this time, 2010, all of the genes were now known for production of fatty acids, for assembly into triglycerides, for packaging those triglycerides in oil bodies that remained stable in seeds and wouldn't break down. And we knew which enzymes could break them down, so we could start to prevent those enzymes from functioning. And so we had the genetics available, and we could obviously transform plants. So we looked at whether, if we took this combination of genes required, expressed them in leaves, would we get oils produced? And this was done by a group of scientists, very smart guys, in my lab in Canberra at the time. Thomas van Herk's paper in 2014 is a good one to check out, and there's subsequent papers by that group. This was the outcome. This is done in tobacco, because tobacco is a very good experimental plant to work with for molecular biology, and it's a high biomass plant as well. These are both pictures of actual leaf cells. The one on the left is a normal tobacco leaf cell. Its energy is stored as quite large starch granules. There's a tiny oil droplet here and there in there. There is oil production in the leaf, but it's usually broken down overnight. It's a transient source of energy. When we brought those genes from the seed and put them in, expressed them in the leaf, we got the result on the right. The cells became packed with oil bodies. The first iteration, we got 15% oil on a dry weight basis, and then we adjusted the genes that we used, and we got to mid 30% oil, which is an amazing result, a third of the leaf weight as oil. If we look at that compared to the seed crops, each bottle here represents 1 tonne of oil per hectare. Soybean, less than a tonne per hectare oil. Sunflower, about 3/4 of a tonne. Canola averages about 1 tonne per hectare. That tobacco crop, if it was a 20-tonne dry weight crop and only had 25% oil, would produce 5 tonnes per hectare of oil, which is equivalent to the kind of average palm oil production intensity. So it's a major step change in oil productivity that we can conceive of here. We had this in around 2017, 2018. And it would have been great to have gone straight to the field with the tobacco lines to explore that, and maybe even to use that commercially. But unfortunately in Australia, tobacco is not allowed for cropping. It's a totally prohibited crop. And so that wasn't an opportunity that we could immediately test in the field in Australia. It is something which could be developed in overseas countries as a production platform, and it's certainly worth exploring, but not at this stage in Australia, unless the government was to change regulations around tobacco cultivation for purposes other than cigarettes, obviously. But the good news is that this technology is very generic, and it can be expressed in basically in any plant. So in CSIRO, we went on to test a number of other species. We tested it in sugarcane, tested it in sorghum, and tested it in potato. And in potato, we tested in the leaves and also expressed the genes in the tuber as an indicator of whether we could produce potentially something like a sugar beet by an oil beet by converting sugar beet to oil production. And it was the technology was effective in all of those 4 species. We would have, on the technical grounds, the expectation that it would work in any plant cell, vegetative plant cell, but that may work more efficiently in some crops than others. So really the task now is to find which crops work best which ones are best suited for our agricultural system or for overseas agricultural systems where they're interested in this technology. We would see these categories: a high biomass broadleaf crop. This could be a tobacco, could be a lucerne, for instance, a perennial legume biomass crop. It could be canola as a byproduct, the crop residue of a canola seed crop could carry oil in it as well. Other brassicas, for the forage brassicas, for instance. The high biomass oil crops, this is a much higher level of biomass production. Sweet sorghum, miscanthus, switchgrass, agave could all be opportunities here. And the third category is in the residual straw of grain crops. So in a corn stover, in a wheat straw, in a triticale straw, for instance. And in the tubers, sugar beet and cassava would be the ones which would be the most likely initial targets. So we really need to get on and work out which crops are best to deploy this technology, and that's going to take some time. I'll just give you two examples of how we might deploy this. I mentioned in the crop residue of a grain crop. So you would know that we have dual purpose feed wheats in Australia, where you graze them during the cooler months, and then you take the animals off at the end of spring and you let it go through to produce a grain crop, a feed wheat. And you can also do that with canola quite effectively as well. So if you can put animals on and eat down that biomass as it develops, you could alternatively cut that biomass, have the oil extracted from it, reuse the residue for it in an animal feed. Could even take the residue through to a different, like a cellulosic ethanol process to fuel, and you could accumulate oil throughout the year. And even if it's a seed oil crop like canola, you can get the oil out of the seed as well. So this is a way of increasing oil production without doing away with the seed production. The seed could be going straight off to food if it was a food grain, obviously. And this would be a good system in southern Australia. The high rainfall zone in Victoria is one where the dual purpose crops are grown a lot. But there are other opportunities in the drier areas of the cereal belt, for instance, and triticale would be one interesting one to try. The highest productivity is likely to come from sugarcane in an Australian context, and we would envisage being able to convert sugarcane into an oil cane. Sugarcane is about 20% sugar in the juice. If we are converting some of that sugar, or the plant is converting some of that sugar into oil, we would expect to be able to generate this type of pathway where in the early stages we probably have an intermediate product which is producing both oil and sugar, and they come out in the juice extract, and then they're separated. You separate off the oil pretty simply, and it goes to the industrial products, and the sugar goes to conventional products. Over time, we would think we could get much more of that sugar converted to oil, so you could potentially have a high oil cane with a small amount of sugar byproduct. And so that is a very useful system for Australian agriculture and for many other parts of the world. So I'm just going to finish up, Jock, with this slide. And the reason is, these are decisions we can make. These are decisions that our policymakers can choose to favour and to support, and we would be able to build the production of this feedstock in Australia, I think, to the level where we could at least supply all of our aviation needs, and beyond that, given the last technology I talked about. So let's just look at the left-hand side. I see that as Horizon 1. If we were to introduce an LCFS scheme that matched the value in competing overseas markets and enabled farmers to benefit by retaining that seed in Australia and crushing it for fuel feedstock, just the tallow would contribute, a couple of 100,000. The canola and cottonseed, I've talked about the volumes there. That probably gets us to 2.5 million. The next horizon would be increasing the brassica oil production, so either expanding our canola cropping Juncias, for instance, Juncia mustard, or introducing some of the cover crops, the camelina, carinata, covercress. That would give another big chunk. If we developed an oilseed lupin, we could count on that, I think, for a couple of 100,000 tonnes of oil. I think over those two time horizons, which is probably out to the end of 2030s, we could get to 5 million tonnes per hectare of feedstock, and that is the maximum we could use in Australia for aviation fuel, as long as it's a 50% blend ratio limit. That will probably change during that period. I think we will go to 100% SAF certified in that period. So the final step is develop the biomass oil crops. It's going to take longer to do, but I would think we could be, second half of the next decade, we could be in production with a substantial amount of biomass oil crops. And if that's the case, the production potential is pretty unlimited. We could go beyond the aviation requirement and start to be fueling marine requirement, and also any residual diesel running vehicles at that time. And if I just put that bar in at the end to show you, that's what's currently in the CSIRO projection for fats and oil feedstock. And I think it misreads the potential that we can achieve if we want to go for it in this way. And I think that's where I'll leave it, and hopefully I've stimulated a few questions. If you want to find out more about the technology, you can just contact me on my email or go to the AgriNew website. I have a couple of articles in there about the biomass oil and also about some other oil technology improvements. And my voice is getting a bit hoarse, so I'll leave it there.
Yeah. No, it's an interesting 20-minute talk, but it goes a bit longer, but I'm glad it did. You covered a heck of a lot of ground and did it very well. Thanks, Alan. We've got a few questions floating around, but I just wanted to make a couple of quick points. Look, this opens up an opportunity for an extra F. We've got food and fibre in the agricultural circus at the minute in production. This opens up the fuel side of things. So it's an entirely, it's the third leg of the tripod, I suppose you could say. And back to Alan's point earlier on, if you don't have the fuel, you can't grow the food. So this fuel, food and fuel security go hand in hand. And at the minute, our fuel security situation is somewhat unpleasant, and 95% imported. If we don't get imported fuel, we cannot grow our food. So logically, we do need to actually address that issue somewhat. But look, I'll just open up to a few other questions. The other comment, Al, I don't think the agricultural diesel use can be sort of taken away. It's one of those hard to abate legacy sort of machine things. 80% of the energy going into ag is diesel based, and it will be diesel based in the majority for the next many years, as far as you can ever calculate. So yeah, there's big issues there that need to be chewed on, and it's nice to see that there's a possible explanation and pathway for all this to sort of get solved.